So, partial derivatives, today will be a fun class. Today will be a very fun class. Maybe one of the last classes you will actually understand right away. Because like the first step in vectors, 1, 3, 0. Oh yeah, it's like this or that. This is also one of the rare cases when you should get it today, right now, you will enjoy it. And partial derivatives are fun topics. They are extremely important, Have you taken ODE class, the ordinary differential equations?
Yes.
So this takes you into the PDEs, partial differential equation class. And PDEs are one of the hardest things to study in math because they are the one who give you equations about how heat converts into energy, how planes fly, everything, and how your blood moves. By the way, there's a called traffic equations, which is the same for blood traveling through your body. They also have blood traffic because cells, when they stuck, just like in a traffic, what it causes what? Yes, a clot. So all of this is described with partial derivatives. You don't have to copy this. I'll write it down by step. Oh, let me sing it for you. I did. Thank you. So, partial derivatives from the title, you can see, means we're going to be differentiating with respect to some variables now. Your brain will get confused at first, and then you'll get used to it. So it should be fine. But the idea is pretty standard. How will you differentiate a function that has many variables? So the answer is depends how you want to differentiate it. For example, let me show you this. This is a nice example. Derivative means how something is changing. We're gonna learn maximum minimum this week. We're gonna do implicit differentiation today, chain rule today. So we take in calculus 1 into 3 dimensions. But in calculus 1 was straightforward. Maximum is on the top of the hill. Where is the hill here? The hill from this direction? Or the hill from this direction? Or the hill from underneath? We're going to learn the different types of surfaces. They will be surface at the top and surface at the bottom. That is also a different idea. That means the slope depends on which direction you're choosing. This is the slope of how this saddle is changing from the point of the head of the horse, right? But what if I want to see how it's changing from this side when I'm climbing up? That means the derivative will depend on the direction, and that's why we call it partial derivatives. So, in practice, it's actually not that bad. When we're gonna do it, your brain just needs to learn how to distinguish, to differentiate what with respect to what. And notation is different, so let's do some example. Here it is. Here's a new notation. F sub x. We don't even put prime anymore. When you do f sub x, people actually know that means derivative. Sometimes people do prime, but that's extra. The wiggly d means partial derivative, so that's delta. Delta f with respect to delta x versus the straight d. Straight d we're teaching you means normal derivative. Curled d means partial derivative. That is what we call partial derivatives with a curl. With the curl. If I'm differentiating with respect to x, I'm going to put x here. With respect to y, I'm going to put y here. With respect to z, I'm going to put z and m and t. So 5 dimensions. Let's find 5 partial derivatives. Let's practice. Consider the function x squared times y plus x times y squared. Let's find partial derivatives. For now, I just taught you 2. And we're going to have like 8 or 10. So, let's find first partial derivative with respect to x. Usually we just keep it like this. If you want it to be pretty, You can even indicate how many variables there are, because sometimes it will be like many variables, gravitational forces and W, you know. So this is actually a very typical problem, to be honest. So for now, we just start with 2. Find the partial derivative with respect to x. The same notation is curly f, curly, and then your variable x. So the idea here is, in your mind, you should now understand and tell your brain, you should, like talking to your brain, tell your brain, x is a variable, whatever else is a constant. And that is tricky because remember there's a joke, where are all the numbers? The upper level classes of maths have like less and less numbers there, 5, 7, they all disappear. We all now use variables. The upper you go, the worse it gets. And then I don't see even numbers, there's x and y. So your brain has to finally admit, x and y can be constant. So when I show you that animation with the slope, this one, this kind of, I will show you again here. We are fixing one of the variables and pretending that is constant. So if I want to find partial slope, so from one direction, I need to fix the other direction. This one has 2 directions, as you can see. See those lines which we just learned, right? Contour map over here. We have 2 types of them, these guys and these guys. Which one do you want to look? If I want to look at these, I need to pretend that others are fixed, others are constant.
Hello, hi.
You just like coming to my classes?
I have an exam after this class.
Oh, I see.
Yeah.
So, that means, let's practice. I'm pretending that y is a constant. If y is a constant, x is a variable. Derivative of x squared is 2x. That is not new. We knew, like none of this will be new. You will just have to do chain rule and stuff. Y is a constant. Constant is glued. Remember, it's multiplied by the variable, so it will be saved. So you copy it. Plus x is a variable. You have to keep saying it in your mind until you get used to it. Derivative of x is 1. Y squared is a constant, so I'm just copying it, squared. This is not a product rule anymore. Do you understand this? Not a product rule anymore. It's a constant times a variable. Constant times a variable. Does it make sense? Because we're fixing, let me make a note, fix y. So y now is a constant, not a variable. Constant, some kind of constant. That's the idea. So we're treating it as a constant. That is derivative with respect to x. What is derivative with respect to y? Your brain now refuses to switch so fast. I'm talking like I know it, but it's actually very common. Your brain just got used to the image, especially if you're a visual learner, that will be a problem a little bit. You just visually memorize x was a variable, y is a constant. Now you have to switch. Now you have to say x is a constant and y is a variable. So who is here, like Jacob's favorite terminology? The main character? Yeah. And then who is not the main character? Please keep saying that. So in first case, x was the main character, others were just constant. Now y is the main character, so you have to switch. Now x is just a constant, so I'm gonna fix x, right? X is a constant, so I'm just gonna copy it because it's multiplied by a variable y. Derivative of y is 1. It's not implicit differentiation or chain rule here. Plus x is still a constant. Derivative of y squared is 2y. No product rule, no quotient rule, nothing. How do you feel about this? Not too bad, right? Not too bad. Now, after this, let me see if the first picture. Yeah. After this, we can start introducing next levels. Why not to do it one more time? Right? So we did it once. Why not to do more? That means we can do upper level derivatives. But what kind of upper level derivatives? We knew there is a y prime prime, x prime prime, f prime prime. Second derivative represents lots of stuff, concavity, acceleration. Do you remember that? How fast the first derivative is changing? Instantaneous acceleration. But with respect to what? So now it's going to be mixed. We can take second derivative of the first derivative with respect to x again, or with respect to y. Y with respect to y, or with respect to x. And in the third case, the third derivative is completely mixed up even more. So let's do it. Let's take derivative of x with respect to x, and that is the notation. The notation with, let me show you the official notation over here, and then you can copy in a second. The notation which we use with delta looks like this. If it's doubled, then you're repeating the same fixation. I would call it like this, same fixation. So for example, that is going to be second derivative of f with respect to delta x, but people don't usually copy that twice, so they put square here. That doesn't mean square, it means twice. Fxx is a second derivative of f with respect to x with respect to x. And then I will want to find a second derivative of y with respect to y, and then I want to find the mixed one. So acceleration now has all kind of the mixed one, x with respect to y. Acceleration now has different meanings. It means, what's the speed of this? This is the first derivative with a fixed one constant. What is acceleration of this speed? Acceleration with what direction? This direction or this direction? And so on. So that has more levels into the differentiation skills now. So let's try it and move on. Your brain needs to learn, especially on a test, to know where to look. If I'm asking xx, I need to find this guy, the first x, right? There's no way you can skip. Unfortunately, I told you in the calculus 1 class, to find upper level derivatives, you almost always have to find the previous ones, right? So I'm looking at this box, and now I'm differentiating the result of this box with respect to x. So I'm fixing x again. Fix x in the red box. Derivative of 2xy gives you what? 2y, exactly. Do you all understand that?
Wait, would you be fixing y, not x?
Oh, thank you. We're fixing y. Good. Yeah. No. You had it right. I had it wrong. Yeah. So we're fixing y. Y is a constant. 2 is a constant. 2y multiplied by x. 2xy prime gives you 2y because derivative of x is 1. Plus, what gives you 1 times y squared? How come it's 0? How do you know?
Because y is a constant.
It's because y is a constant. Maybe it's pi or like 2.30. Does it make sense? How interesting is that? Now, fyy. From all this math, you need to locate where to look. I will look over here into this green box where we fixed x because y is a variable. So I'm gonna fix x one more time. Fix x one more time. I'm looking at the green box. Y is the variable. X squared times 1 gives you 0 plus 2xy gives you 2x, which one? So y is a main character. Everything else is not. 2x. 2 times multiplied by x times multiplied by y. Y is the main guy. Others are, how would you call it? Side characters. Constants. Okay, the official should be constant. Right? Did you understand this part? So I heard yes, no. So let me try to explain more. For the fyy, I'm looking at this box. And this box is This time I will put everything in black color. It might explain actually better. X squared plus 2xy. This is what used to be the first derivative with respect to y. I'm looking at that thing. Now, either with my mind or with color coding. At first, color coding helps a lot, and then you get used to it. The first y tells me where to look. So I found f with respect to y. I located it. In my mind, I fixed it. The second y tells me who is the variable and who is the constant. The second y says y is the variable. Everything else are constants. I'm looking at this and I only see one y. So this is the only variable here. Everything else are constants. X squared being a constant gives 0. 2x is a constant multiplied by the variable y. Derivative of that is 2x. How about that? Yes.
So if they're both constants, then why are we only keeping the 2x?
Oh, good question. Remember, derivative of 5 plus x prime is 1, while 5 times x prime is 5. Remember that? So if 5 is multiplied by x, it's called rate. 5, like a sticker, sticks to the variable. When you take derivative of that, it should survive because it exactly answers the question how fast x is changing. 5 is multiplied, so it gives you a rate. 5 units fast. But if 5 is added, that's the constant standing isolated. Isolated constant has speed 0. That's why it's called constant. It's constant all the time. Speed of the constant is 0, so it's 0 plus 1. Does it make sense? So that's kind of like the review from Calculus 1. That's what I was teaching last week in my other class. So multiplied constant by a variable survives. Added should be eliminated because the speed of the constant is 0. Yes?
But in the case that you have there, the 5 plus x, the reason the 5 goes away is because it doesn't have a variable, right?
Yes, because it's standing isolated. Yeah,
Right.
exactly.
So why is the 2x or the x squared going away?
So
If
x
you have the
squared is
2,
a
that's gonna go in
constant.
front of it.
X squared is like this 5. When I'm differentiating with respect to y. This is exactly, she's right, this is exactly where brain is refusing to see that x is a constant right now. How do I know? Because of this notation. Derivative with respect to y means I'm treating everything except y as not important constants. So x squared here is like 5 over there. Derivative of x squared is 0. 2x is like 5 multiplied by the variable. So they are also constant and they will stay. Derivative of y is 1. What do you think?
Okay.
This is exactly like this hard moment to get used to it. And then when you do, I promise it clicks. At some point it clicks. And it's pretty creative what we do here right now. I can color code again if you want. When we fix this phrase, fixing x, this phrase I wrote here, fix x means, oh, this might help you. Imagine x is 10, some random variable, doesn't matter, why 10. Imagine x is 10. X squared is now 10 squared plus 2 times 10 times y. This should help you to take the derivative easier. Derivative of that is now 0 plus whatever that constant is, 2 times 10. Make sense? So maybe at first couple times, just actually imagine some concrete example, 10, 1, whatever it is. And that might help you. The fun one is this one. How about this? The mixed one. So how to read this notation, f, x, y. First of all, the notation will be different. The first partial derivative was taken with respect to x. And then, let me make sure I'm consistent with the book here. Yeah. And then we're taking it second time. This square is not square, that means second derivative. But I cannot put second here because it's not with respect to x, with respect to x. I'm putting second one with respect to y. This is a typical notation for the second derivative of your function with respect to x first and then with respect to y. This is a short notation which I like more. With respect to x and then with respect to y. This is not a product, it's an order. So how should I solve this? If you see this in the test, in your homework, whatever, this is how you should see it. You first need to find derivative with respect to x, step by step, right? We found it, so the first x just helps you to locate the needed derivative from all this list. Where is it? The very first one in the red box. The very first in the red box, this is where I will be looking at. So the first variable tells you where to look, and it says, look at the red box. Also this one tells you where to look. The second one tells you who is the main character here. Y is a variable. When y is the variable at this point, just like in the previous example, I'm fixing x, right? Fix x. So imagine x is 10 or whatever you want. I'm looking at this first box. This is 2xy plus y squared. So even though you see 2xy plus y squared, you see that we are treating y as an important person and everything else are just constant. So maybe just choose x to be 10. What you see is 210y plus y squared in your mind. Say it out loud in your mind, it might help you. What is the derivative of 210y? 210, right? So it's going to be 2x. 10 is just example. X is a constant, remember that. I'm fixing x. Plus y is the variable. What is derivative of y squared? 2y. How about that? What do you feel about this? One missing from the whole list. So you will have in your homework find all partial derivatives of the first order and second order. Which one is missing? Fyx.
That'd be the same thing.
We'll see, maybe not. Fyx. But you still need to get used to how to treat the notation. Fyx. Did you guys see this topic in your physics class?
I don't know. I never did.
Or any other class? So,
They did the derivative for it.
yeah, surprisingly it's not synchronized, and some of you already have seen it in some other classes. So this notation tells you we want to take second derivative of the function f, and to get into second derivative we first took the derivative with respect to y, and now please take it with respect to x. Okay. The first variable tells me where to look. The derivative with respect to y. This is the green box. The second variable tells me what is important. Since x is the variable, I'm fixing y. Y now is a constant, say 10 or 1 or 7. I'm looking in the green box, or even the one on the right over there. I have x squared. I have x squared plus 2xy. They're all in black color. Your brain needs to handle distinguishing which one is important and which one is not. X is the variable. How do I know? Because of this notation over here. So x squared gives me 2x because x is the variable. 2xy, in your mind, you keep reminding yourself, x is a variable, 2y is a constant. So the derivative is 2y. Do you agree?
Yeah.
They did match, which is a theorem. This is actually, so let me write down. Note, partial mixed derivative x and y match if the function, if f of x and y is continuous. Continuous. For continuous functions, they do match, which is good. Yes.
So for like 5 and 6,
Yes.
for I mean, I don't know if this will work long term, but I just kind of did it where I took like the derivative of x, right? So we already had like for the derivative of x, we had what 2x times y plus 1 times y squared, and then I just took that, and then I just took the derivative of y from that. Does that work long term, or is that just kind of like a
result? What is?
Well, I got the same answer. I got
Yeah.
so
That
like
is the thing. They will match. The function is continuous, so most of the time they will match.
okay.
Good job. I don't know if I should take points in the exam or not if you took the wrong derivative. The answer is the same. You should be careful. Some functions are not continuous. For them, some functions are troublemaking functions, like step functions, piecewise functions. They might not give you this theorem. It's a theorem, actually. But in general, you're right. These two will matched. So he's right. Like whatever your brain likes to take the derivative with respect to take that, and they will be the same. And actually, it also goes to the upper level. X, Y, Z, Z, Y, X. They also match if functions are continuous. So that is note. One more note. It goes to the upper dimensions as well. If functions is continuous, then X, Y, Z will be Z, Y, X. Those are derivative. Y, Z, X, and there are more, right? So there are more derivatives. The higher you go, the crazier it gets. Or X, Z, Y, Z, X. Anyway, there are more different derivatives and stuff.
What about x, c, y? That doesn't mix it up.
Yeah. The answer is yeah. It will be there. It will be interesting. Let's practice with some stuff like exponential functions and possible product rule and chain rule. Yay! Also implicit differentiation. X, a function of 3 variables this time. Now your brain will get super weird because now you have X, Y, and Z. All of them at some point can be a constant or a variable. The main character and not the main character, right? So X is multiplied by e to the y z. Let's find those guys, the derivatives. The first derivative with respect to x, in this case, I like this screenshot because it's color coding. When I'm taking it with respect to x, x is the variable. Everything else is a constant. So you can even tell your brain, oh, y and z is like 10 and 5. So what is the derivative of x multiplied by e raised to 10 and 5? What? E, so what do you think? E to the y z. Yes, good job. I heard weird answers, but I got what you mean, 10 and 5, yeah. Does that make sense? That is like x multiplied by 10, right? Or like e to the 10 or whatever. So this is like good point to stop. Tell me, does it make sense? X is a variable. E to whatever it raised is a constant. It's like e to 17. So the derivative of that is just e to whatever it is. With respect to y, it gets more interesting. Now y is a variable, right? So x is a constant and z is a constant. Is this product rule or not?
Sure.
Not yet. We're gonna get product rule soon, but not yet. X is a constant. X and z are constants. So this is also good notation, by the way. Parentheses, and then x over here. That is also a decent notation saying we're taking derivative. Sometimes people put even prime over there. Sometimes. So with respect to y, x survives because it's multiplied by a variable. What kind of variable? E raised to the yz, where y is the variable. That means there is chain rule going on times the derivative of the function in the exponent, which is times z. This is getting interesting. How do you feel about that? Slowly. Y is the only variable here because we chose it to be like so. I told you take the derivative with respect to y. Here it is. x is a constant. Maybe it will be easier for your brain if you imagine it's 5. 5 times e to y is 5 times e to y. Remember, the derivative of e stays derivative of e. But y is multiplied by constant z. Chain rule tells you copy and then multiply by the derivative of the function inside. So let me put a note. This is chain rule, your favorite rule. Chain rule that says look in the exponent and see a constant there. Y is multiplied by z. Z is a constant, so derivative of yz will be z. Okay, maybe it was not as straightforward as I expected. Somehow, that was my favorite topic when I was learning this. I don't know why. I really liked how my brain had to switch. You know, there was a movie when they were showing that the cards, so hearts are red and so on, right? But what if hearts are black? And your brain immediately refuses to accept that. Why hearts are black? But why should they be red? And this is exactly what we're doing here. Your brain should switch from getting used to x or y as a variables all the time. No, I can give you a list of 33 letters of Russian alphabet, and they all may be English, Russian, Latin, variables, or constants. So you have to get used to it slowly. Especially with physics and engineering major, you have to get used to it. Yay. Last one, z is a constant. No, z is a variable, everything else is a constant. It will be almost the same as the previous scenario because x survives since it's multiplied and it's a constant. E raised, you should copy when you differentiate exponential function, and it's a function. How do I know? Because z is a variable, so e to the z is a function. But then chain rule happens. Chain rule happens again, and it tells me, look at the exponent. There is a variable times constant there. My brain now should switch. My brain should say, oh, z is a variable, y is a constant, so multiplied by y. How about that? How about that? Not too bad. People are like, oh my gosh, what is happening? And this table shows you all the typical ones. So you don't, I'll give you as a note, but that's exactly what we did. So second derivative with respect to x, there are several notations. Parentheses are not very popular, but these ones are popular and these ones are popular. And this first one is popular. Second derivative with respect to y. Mixed second derivative. Sometimes people call it mixed one. fxy and then fyx. The first, that is actually not correct as I can see. The first one should show you what was the first derivative. So this is actually yx. They are mixing it up a little bit. I'll fix it later then. The first should show you what was your first derivative. The second tells you what is your second derivative. Here's a nice explanation. Here's the shape. Make a sketch if you can. This is a very nice picture. Here is a surface. Say it's the beautiful roof of some kind of modern building. Here's the roof. This is a line of the slope. But what kind of line of slope? What direction? We have curves here, right? Directional lines here and here. So we need to fix. There are two directions here, x and y, and z goes up. So we need to fix to see where do we want to go. By taking derivative with respect to x, I'm fixing y. Y is this direction. So this direction now will be fixed, while x will be changing. See? So I'm choosing one line out of all of them, right? Contour maps and so on. This is the same thing. Those lines, contour lines, right? So this is the one I'm fixing. How do I fix it? Let me write it down. This green one is fixed because I'm fixing y. How do I know that I'm fixing y? Because it says, let's take the derivative with respect to x, right? With respect to x. So x is changing, and indeed x goes left and right. By y is not changing. Y is fixed, some kind of constant. That's it. That's exactly the very good explanation here. When we're fixing a variable, that creates one unique path from all of those different ones. We're fixing one. Then this derivative will give me the equation of this tangent line. We know that. And at the point, it gives me a slope. We know that. And this point is location A, location B, and the height f of A and B. We know that. X, Y, Z. That is the idea. And the slope gives me lots of information, increasing, decreasing, maximum, minimum. In this case, in this particular point, we're decreasing, we're going down. Even though from this direction, we're increasing. And that's the cool idea of the 3D shapes. If I'm hiking the mountain from this direction, I'm actually hiking down right here. So this derivative I'm expected to be negative. But if I'm hiking it from this path, I'm actually climbing it up. So at this point, with respect to y, the derivative will be positive. And that is why it's fascinating. Because from different directions, I will have different results. Did you just notice what I said? Decreasing from this direction, but increasing from this direction. And it will be third direction and fourth direction. And all of these matter. So that is my point to show you. Here is a difference. What do you fix? Look at the point. This is the graph 4 minus x squared minus 2y to the 4. Depending what you fix. If you fix y, then you have the red line fixed. If you fix x, then you have a blue one, and so on. Different derivatives give you different results. So increasing, decreasing from this point of view, or increasing, decreasing from that point of view. So that is interesting. And that's how we're going to be looking for maximum and minimums. Look at this. The plane cuts through when I fix the direction. When the plane cuts through, the red color gives you those particular curves. And then at any moment, I can now find increasing, decreasing, maximum, minimum, local maximum, global minimum. So that means the moment I fix one of the variables, other is the variable, and everything else are constants. So these are projections with the fixed variables. That is pretty cool. And this is exactly the screenshot I took. When you fix one variable, you're creating a slicing plane. Plane now is scanning through the 3D object only towards one direction. When you're fixing the other plane, that plane will be scanning your object from different directions. CAT scans your body this direction, that direction, up and down, right? So that means it's fixing a derivative. Fixing is a variable and taking different derivatives. Okay, so this is kind of the big idea here. I like this pun. Partial derivatives. It's partially derivatives, but a whole lot of fun. Like, yeah. I'm not good with puns, but I kind of get it. I don't know. Maybe you like it. Anyway. So I kept, did you get it? It's partially derivatives, but a whole lot of fun. You know I'm not good with puns. Getting puns is like an upper level of understanding language and the culture, so I barely understand any puns.
You're almost there.
No, I have 2 favorite puns, if you want to know. Let me see. What is the favorite letter of the pirate?
R.
No, it's the C.
Oh, that's actually a good one. Oh, shoot.
I really like it.
Oh,
And the second one is not good as the first one. I only know 26 letter of English alphabet. I don't know why. There's like others like, well, what the owl say? Whoa, like what? I never understood this. Others are complicated. You also need to understand local culture to like understand the puns. So like, not very.
I'm down with myself right there. I remember leapfrog.
Okay, implicit differentiation. Pom pom pom. Your favorite topic, remember, was implicit differentiation? Implicit and chain rule. Let's try to fit both topics today if we still can. Oh, maybe not. So, implicit differentiation. Let's have a function x cubed plus y cubed plus z cubed equals 6xyz. Wow, okay. Well, look at this. So any derivative I can ask you, you have to learn how to find it. That from now on, you're a specialist in taking derivatives. I will ask you some random one, which is just the one in my notes. So it's the function with respect to x. Okay. I want to find derivative, so I want to find z prime, right? But do you remember what implicit differentiation stands for? Since z is not written like blah 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 blah, f of blah blah blah, I cannot easily find z prime. So I cannot find it explicitly, and that is why I will do it implicitly. Question? Yeah.
Is that a 6 or is that the swirly thing that you have in front of
Yeah, thank you for saying. 6. I will try to keep in mind this, yeah. The swirly thing is the other way around. But actually, you're right, there is new, so there is also a thing like that. Yeah. New, and there's a mu, you will learn it soon, and so on. These most complicated are phi, psi, and xi. These are also famous trio. You will be learning them in physics and upper level math. Yeah, but we will have integrals phi and theta
I like the pitchfork one.
and the rho. Yeah, the pitchfork actually is cute. I like it. So, let's do it. We will differentiate implicitly because we cannot do it explicitly. We're keeping in mind that there are two variables in this case. How come? What did I just say? 2? That is weird. Tell me why. Tell me why. Dun, dun, dun. Because, good job. Because z depends on x and y. That is chain rule. Pum, pum, pum. So z is the variable and x is the variable. X is independent variable, z is dependent variable that depends on x. So you remember implicit differentiation says treat one normally and the other one as chain rule. Let's do it. Now your brain is completely messed up. So x is the variable. Derivative of x cubed is 3x squared. Agree? Y cubed is a constant. Derivative of constant being isolated like so is 0. Agree? Z is a variable, dependent one. So what? It's fine. So we're treating it as not a constant. Derivative of z cubed is 3z squared times, chain rule tells you, implicit differentiation. Z prime, remember that's how I was teaching in calculus 1? But now this notation is bad because z prime does not represent z prime with respect to what? So you either put it x over here, or you do a beautiful notation with the curly d, derivative of z with respect to x. I was mentioning calculus 1 that in calculus 1 you could put prime 1 and it would be fine, but in calculus 3 it will matter with respect to what variable you're taking the derivative. Because z is dependent variable. And in technical speaking, remember, we're actually looking for this part. That's exactly what they ask us to find. We're looking for this part. Yes?
So is that a part of the equation just because we have that z equals z?
Yeah.
Okay.
Do you know how I know? Not just from my notes. The moment they ask me find derivative of z with respect to x, that tells me two things. First thing, z is a function. Second thing, x is a variable. Everything else is a constant. That's how I know. Z is a function, so I'm treating z as a function that has x inside of it. So it's chain rule. Now, equal sign. What is the right-hand side? Is it product rule or not? It is.
Yes.
Because z is a variable and x is a variable. So it is product rule where z and x are variables. Now you can try to distinguish any kind of possible way you want, maybe like so, or 2 and 2, whatever you like, to be honest. So, for example, I will do it like so. U times V. Product rule, let me write down. U times V. Product rule. That's how I was teaching in my classes, using U and V. Product rule. So derivative of U is derivative of 6xy. 6xy, where 6 and y are constant, gives you just 6y. That is derivative of U. Remember product rule? Anyone remembers that product rule? Derivative, not derivative, plus not derivative, derivative. That's how I'm teaching it, at least. Like so. So, this is just U prime. Copy V. V is Z, so I'm just copying it. That is V. Plus, copy U. That is 6xy times. Copy, the derivative of Z is Z prime. But we just realized that Z prime is a bad notation, so I'll write down dz with respect to x. That is U V prime. How about that? No, it's fun. I kind of hoped you will enjoy it, to be honest. Now we're almost done. We need to solve for that fraction you see. dz over dx, or z prime. How did I teach you to do that? I was teaching it in steps. Relocate things that involve that derivative into the left-hand side. Everything else move to the right-hand side. So, and you can even skip the step. Do you remember how to skip the step? You factor it out at some point. 3z squared times dz over dx minus 6xy dz over dx. So I'm relocating important things to the left-hand side. That is not a requirement. You can put it to the right-hand side. My point is we're trying to isolate dz over dx. Everything else is garbage. Move it to the right-hand side. 6yz minus 3x squared and minus 0. So everything else, are you like going with garbage? Put it to the right-hand side. Now factor out. So step 2, when you move, step 1, differentiate. Step 1, differentiate. Step 2, move important things to the left, not important things to the right. Step 3, factor out. dz over dx, open the brackets, 3z squared minus 6xy, close the brackets, and you have right-hand side on the right-hand side. I'm just too lazy to copy it. Step 4 is the answer. And it always has the same look. Equals right-hand side over those brackets. That's kind of the whole idea. We're trying to isolate the derivative because that's what they ask us to find. So it's going to be right-hand side is 6yz minus 3x squared all over 3z squared minus 6xy. Put it in the box. That is your derivative of z with respect to x. This is implicit differentiation in the multivariable calculus. How do you feel about that? It's not too bad if you are not too sleepy, not too drunk, not, you need to be concentrated not to miss anything. Your imagination should work, and that's why this chapter will really train your brain really well. And that's partially why I like it so much. Concentrate and do the homework.